All right, so let's do the more exact solution to the electrostatics. Let's look at this in inversion layer again. We're not interested in currents, right? No current flow, but we do need to do Poisson equation and solve that and do this in some detail. Now, we had derived this expression using the depletion region approximation, where psi s goes as, the gate voltage goes first as psi s square root, and then linearly in psi s. Okay. Now, let's calculate this. We know that we have a EC. EC is some constant minus our applied surface potential, psi of x, okay? So we define it as such. So here we have our potential, and psi x is our EC in bulk minus EC with the internal potential, and we divide out the Q. We're defining some normalized variables, just like what the title said. And we'll do the same, we'll do now a normalization of the psi x to kt over q. Okay, so we're basically dividing out kt over q out of our terminology, so we don't have to carry so many symbols around, okay? So we redefine our psi x into some u, and then we also have the value at the surface. That's the surface potential. Same expression, but now at the surface, x equals surface, or x equals 0, right? Same thing here. And then we express the Fermi level as well as a UF, where we now carry this through as a function of bias, position in the device. All right, so we have these redefined terms. Now we're going to write down hole densities in these terms. So hole is Ni times exponential Ni minus IF, same as before. We can redefine this in this UF and U. Same with electron density, which is just minus Nix minus EF, same term. We can do this for the donors that are exposed and also the acceptors. Now, we carry this through either for donors or acceptors. So far we only have done this for acceptor doping, so we're p-type doped here. We'll continue that, but you can calculate this in general for either N or p-type doping, and we'll go through an exercise later where you do this numerically, or the recipe for doing this numerically. All right, now we need to solve this Poisson expression with the terms for p and doping and the doping, and we can plug those in, right? And we get an expression with these newly formed units of U, F, U, and U. Okay, and we will end up with a differential equation that is now in these U's. And the right-hand side is some coefficient, a function of U and UF. And you can code this expression up, right? You can discretize space and evaluate this term computationally, okay? So this can be evaluated for any given U if you want to. You choose a Fermi function, and you can generalize this problem as you wish, okay? Now, what we're ultimately after is integrating this potential, right? We know that U is related to the electric field, okay? We know that the gradient of du dx is related to the electric field. And we roughly have an idea what the electric field is in this triangular notch, okay? So we'd like to get from the second derivative du dx squared to a single derivative by a form of integrals, okay? Now, if you go way back when to high school, remember when you differentiate the square of a function, what do? You say you want to take ddx of some function squared, okay? So you pull down the square, the exponent, reduce the exponent by 1, leave it alone, and then differentiate the inner part of the square. Okay? So dx of du dx squared is 2 times du dx times d dx of the inner part du dx. Remember that? Now, I just multiply this out, that this is 2 times du dx times d2 du dx squared. Why am I going through this? Well, this is what I have here and here. I'm going to multiply left and right hand side of the equation with 2 times du dx. Okay? And if I do that, I can use this term here, right? There we are. And I'm multiplying one more time with dx. Okay? So I haven't done anything to these expressions except I now can pull a trick, an usual integral trick, where I want to integrate this equation up. Okay? I've also introduced that term here that called the Debye length. Okay? So LD squared is here in these terms. Okay? And that's the length over which the carriers are going to be decaying or screening each other in this layer. Okay? All right. Now I can integrate up this expression over dx. Okay? And I do this over here, where I'm integrating this term here, and I get rid of this dx and this dx here, and I can just integrate the du. Okay? And on the right-hand side, I integrate this over du, because I got rid of this guy. Okay? So far, I haven't done any work. All I've juggled is symbols around. Okay. Now, I can do this integral now. And I do this against the graph here starting from infinity, where I know I have 0 field, and I integrate up from the right into my electric field as a function of s. And I end up with this term here, and boundary condition at 0 is that there is no electric field. I can't quite do this integral on the right. I have to do that in general numerically, and we'll work on the recipe on how to do this numerically in a minute. But I can write this down for the surface. Okay, so at the surface I know what my electric field is at the surface, and it's some function, this f at the surface now, and uf. Okay? Now, I can express, again, my gate voltage as the surface potential here plus the capacitor expression I had before with the electric field. Okay, that's the electric field dropping off over the oxide. Okay? And now I have that as this uf, this function, this complicated function f. Now, it turns out that here you have the psi s, and the approximation that we had come up with before, which was the depletion region approximation, which gave us the square root of psi s. The exact expression is buried here in this f. Okay? Now, to get this correct or exact, you'd have to do it numerically. And we'll walk through that calculation in a few minutes. All right, how would you do this numerically? Well, you can set yourself a surface potential, pick a value, and calculate US as like this, where we have a recipe, right, for US that is relating to psi s, and divide the space into endpoints. Discretize your x direction into endpoints. Okay? Make it large enough that it's you can resolve the numerical quantities we'll show you, I'll discuss how many points you might need in a minute. Calculate the G, which were just expressions of complex exponentials, or exponentials at all those points, and integrate that to find F. And once you have that, you have VG. And that relates your psi S to VG. Okay? And that's how you get this exponential growth in psi S, and see how those two are related. Now here are some examples of an exact solution. So on the left you see now the charge in accumulation. Okay, so you have hole density piling up against the interface very narrowly, and the corresponding U is distributed like this. Okay, so that's your band bending in the semiconductor under accumulation. Now, if we carry this forward, now we go towards depletion, we get a distribution of charge that looks like this on the top, and it resembles our depletion region, except it's smoothing it out in X. Okay? And the electrostatic potential U that you compute is smooth. Okay? Let's look at the value here. You have some nominal value of 20. That's normalized. Remember, we took out all the KTs, etc. That makes life a bit easier, right? And the amplitude here is involving the excessive doping. Okay? So it's 1. You really do deplete the carriers up to the depletion region view, but then it's a smooth function. Now, if you begin to drive this just over inversion, right, over towards inversion. So exactly at threshold, you define this to be, well, this needs to be 2, right? We said that if the electron density is reaching an amplitude of the acceptor density, that's what we call threshold. So if the peak here reaches -2 as normalized by the acceptor density, that is threshold. Okay? So you're seeing the charge pile up against the interface, and now you see here we were so at half, units of half, you see all the depletion happening. Okay? Now, if we go into strong inversion, we really have a ton of charge against the interface. And it's normalized going down to values of -400, okay, here. And the U only went from 20 to 28 or so, okay, or 25 to 30. Okay? So the point is, with very little change of U amplitude here, you got a ton of additional charge, just like what we had sort of waved our arms about, okay? Now, if you do this numerically, this is going to be really challenging. I suggested that you can discretize your domain here, right, like this, and calculate the G and integrate to the F and get that, right? But if you wanted to resolve this spike here, you're going to have to work really hard. And all the semi-classical device simulation tools that are out there, they do this calculation. They are programmed to do so. But you have to do spatial meshing to do this resolution right here. And I remember going to my first conference at TI. I was just out of grad school, more or less a year then. I started to work at Central Research at TI. And they had this internal research conference. And that's where the research guys like me would meet with the really applied guys that were running these simulators. And this is now 95, 96 ballpark. And they were struggling as they scaled down the oxides and try to understand and model in detail the charge in the inversion layer. So I saw a talk by a person on the applied side who runs these simulators on how they modify the simulator to put in enough nodes here numerically to resolve this spike. Now, they had to put in so many spatial nodes, they put them so dense that they're subatomic. Right? Subatomic resolution here to resolve this. And I was there with my best friend Chris Bowen. We were both on the research side, and I said, no, this is totally wasteful and it's completely wrong. Because you can't have subatomic sheet charges like this, okay? And we'll talk about that in a minute. Okay, this animation shows that when you go in depletion, you can change significantly the U. You go from 10 to 20. So that translates into significant potential changes in the semiconductor still as you apply a voltage. But as soon as you hit threshold, you go from 20 to just a mere 28 or so, okay? And all the charges that you now are inducing in inversion do not cause more potential drop in the semiconductor, but most of the potential drop will be in the oxide, okay? And therefore, you basically are controlling the charge in the semiconductor now if you're in inversion by completely just dropping the potential over the oxide. So okay. All right. So now we're getting to the, is this really exact? Okay. So if you're really having a strong potential like this, and you made your oxide very thin, where you now induce a very strong triangular well in here. Okay? Do you really have classical charge in there? No, you have quantum confinement, okay? There's a wave function that sits there rather than semi-classical charge. So you need to account for that. Effectively, you have a increased band gap, if you will, because you have a confined state here. In the transverse directions, you have parabolas still you need to integrate over. So you have 2D band structure rather than 3D band structure you need to integrate over. And you might have multiples of those states that you need to integrate over. Okay. Also, you don't have a non-degenerate semiconductor statistics, so you really have to compute the Fermi function properly as well. So, that being said, this becomes really relevant for really scaled devices, and you have to do this well. So there's a paper, I just mentioned my best friend Chris Bowen here, where we started to calculate this in '97. So a year or so after I had my encounter at this TI conference, right? So people are really interested in calculating the states in a silicon dioxide heterostructure like this in the channel, right? I mentioned to you the states, but the issue is they couldn't even properly treat all these states here because it's the incorrect density of states because you really have a semi-open system. So the states are properly resolved like this, where you have a continuum of states on the top of the barrier and you have these discrete states down here. And then you still have to integrate over 2 dimensions in this direction. Okay, so you're injecting carriers or tunneling from quasi-bound states, and you're injecting and tunneling through a continuum of states. And you have to treat it in the same simulation. And this is where the quantum transport simulation comes in that we did at TI. Also, you not only go from electrons of what I just showed here, you can also see that you have under high bias tunneling right here out of the holes. And that surprised people, because that explains some interesting results, some kinks people saw in the IV curves here. And this is the tunneling not only of electrons, but also of holes. And this was one of the first simulations that really showed it in a full quantum transport approach. And ultimately, we can match capacitances. So here we did this for current flow. So this is current, tunneling current. But what people are really after is measuring properly capacitance. So with properly doing the density of states and the filling of the states, you can get to the capacitance. And we'll talk more about the shape of these capacitances in the next section. So with that, I'm going to conclude this section that we've calculated the induced charge in depletion and inversion as a function of gate bias and found that tunneling current and you need thermionic emission theory, or you do a full quantum transport like what I showed you at the tail end here. And the exact solution is quite complicated, and you probably need to do this numerically. But even that is not quite exact, because it treats charge as a classical distribution and not as a quantum distribution with wave functions. So that concludes this section on the electrostatics of a MOS capacitor. And in the next segment, we're going to talk about capacitance values at high and low frequencies, etc. So I'll see you at the next section. Thank you.